Alright everyone, so we want to continue our conversation on using derivatives for various different applications. The next thing that we're going to do is use derivatives for what are called optimization problems. So we're going to use these for finding maximums and minimums in more word problems now. Okay, so the main idea that we're going to have is that we've got some constraining equation constraining quantity, and we want to maximize or minimize something else that is related to this constraining quantity. So an example of this might be that you want to maximize or minimize an area subject to a constraint in the perimeter. Okay, so a simple example of this. So suppose we want to maximize the product of two numbers, and we require that these two numbers sum up to 13. Okay, so we want to see how we could go about doing this. Well, one thing that we might think to do is just go and start making a table of values. So go and take various different numbers that sum up to 13 and see what you get when you multiply them together. And from this, we see that we're getting the biggest product when our numbers are 6 and 7. And that's great if we were restricting ourselves to integers, because if we're restricting ourselves to integers, it's kind of straightforward to do this. But nothing in the statement here says that we can only have integers, so we actually need to consider any possible number. Okay, so we can go and look at it like this. We have this function that we want to maximize. It's a function of two variables, x and y, and the function is just the product x times y. But we also know that x plus y has to be equal to 13, or another way to say this is that y has to be 13 minus x. So from that constraint, we can eliminate a variable from the function we want to maximize. So we can replace y with the expression 13 minus x. So we can reduce the original function f down to be just a function in one variable, and we'll get 13x minus x squared. Okay, so then the next thing that we're going to want to do is we're going to want to find the critical points for this function f, and we'll do that with our derivative. So we get the derivative is 13 minus 2x, and because we're dealing with a polynomial, we know that our derivative is defined everywhere. So we get that our derivative is going to be 0 at 6.5. Now, the one thing to keep in mind is that we said we want to maximize our function f. What we found so far is a product, we found a point that will be a critical point for this product, but we don't know whether it's a maximum or a minimum. So that's where the second derivative is going to kick in. So what we want to do is evaluate the second derivative at our critical point. For this case, the second derivative is minus 2, so the second derivative evaluated at the critical point 6.5 is clearly negative. And from what we said last time with the second derivative test, that tells us that our critical point is going to be a local maximum. So whenever we do one of these kind of problems, we have to verify that we've actually found the thing we want with a derivative test, but usually the second derivative test is the one you want to do because it's just easier. Okay, so that tells us that the maximum for this setup is going to be 42.25. Okay, so here's kind of the approach that we want to do, and it's very similar to the approach that we had when doing related rates problems, but it is slightly different. So what we'll do is we'll first read the problem carefully to figure things out, just like we did with the related rates problems. Make a sketch if need be, and then define anything that we're going to use that wasn't given to us. Okay, and then here's where the differences start. So we need to express the quantity q that we either want to maximize or minimize as a function of the variables that were given. And then what we're going to do is use the constraining equations to knock out all but one of the variables. And then after we've reduced the function down to something in just one variable, we can start differentiating to get our maximum or minimum. And then at the end, we just need to verify using a derivative test that we've actually found a maximum or minimum, depending upon what we're looking for. And then we'll just give a concluding statement. Okay, so we're going to do a couple of examples of these. So the first one that we have is we're given a rectangular enclosure, has to be constructed along one side of an existing wall, so a barn or something, and the other three sides are going to be fenced. So if we're only allowed to use 100 meters of fencing, what is the largest possible enclosure that we can have? So we have a restriction in the perimeter, and we want to maximize the amount of area. Okay, so we have this barn, and it's just there, and we're going to build this fence around it. So we're going to have three sides that we're going to use. So we're going to have two sides of length L and one side of length W that are going to have to account for our fencing. So the function that we want to maximize is the area, so we want to maximize the length times the width. And the constraining relation that we have is that 2L plus W has to be 100, or W is 100 minus 2L, and then we can use that to go and knock out one of the variables in the area equation. So we can reduce the area equation down to a function in one variable, 100L minus 2L squared, and when we take that derivative, we get that a prime is going to only be 0 at 25, and also it's a polynomial, so no places where it's undefined. Okay, and then as before, we could go and verify with our second derivative to see that our second derivative is going to be negative everywhere. So in particular, it's negative at our critical point, which tells us that our critical point of c equals 25 is a local maximum. And then all we're going to want to do is just go and put the critical point back into the original function to get our area at that point. So we'll get that the largest possible area that we could get is 25 meters times 50 meters, so 125 meters squared. And again, the units can also help make sure that we've got to the right answer. Okay, so for the next one, we're going to have a lighthouse located 5 kilometers north from point A on an east-west shoreline, and we're going to have to lay a cable from the lighthouse to some point B that's 10 kilometers to the east of A on the shoreline. And the cable is going to be laid through the water and then also possibly on the shoreline. So we're going to put a point C somewhere between A and B on the shoreline. Then we're going to have the cable going from L to C and then C to B. And we're told that the cost of putting the cable through the water is going to be $5,000 per kilometer, and along the shoreline it's going to cost $3,000 per kilometer. And what we want to do is place C somewhere along the shoreline so that we minimize the total cost. And then we'll do this problem again where we change the distance from A to B to only be 3 kilometers. Okay, so the first thing that we'll do is we'll set up this problem. So we'll take the distance from A to C to be given by the variable x, and we know the distance from A to L is 5, so that tells us the distance from L to C is going to be the square root of 25 plus x squared, and then the distance from C to B is going to be given by 10 minus x. So from this, we can make a cost function, and maybe I'm choosing a bad variable here, but with C, but it should be clear that here c of x is a function for the cost, and the original c was a point on the map. Okay, so our cost function is going to be given by $50,000 times the square root of 25 plus x squared, so that's going to give us the cost going through the water, plus 3,000 times 10 minus x, which is going to be the cost going over the land. From there, we're going to want to find our derivatives, so I've gone and taken the derivative for us, and it's 1,000 times this expression in the parentheses, 5x over the square root of 25 plus x squared minus 3. And what we could find is that the critical point is going to occur at 15/4. The derivative is also going to be defined everywhere because that denominator, or the square root, is always going to give us something positive. Okay, so what we're looking for here is an absolute minimum, because it is possible that we could be placing the we could make x 0, we could make x 10. So we're looking for the minimum over that kind of confined range. So all we're going to want to do is take this critical point that we found of 15/4 in addition to our endpoints of 0 and 10 and put them back into our cost function. So when we do that, what we see is that at 0, so if we just went and put the we just went from the cable from L straight down to the point A and then along the shoreline for 10 kilometers, that would cost $55,000. If we took the cable all the way through the water from the lighthouse straight to the point B, that would cost just under $56,000. But if we go 3 kilometers to the east of A and then 7 kilometers along the shoreline, that'll cost an even $50,000. So that's going to be where our minimum is, and that's going to be the point that we're going to want to take here. I guess the other thing, because we're finding an absolute minimum here, we don't actually need to worry about the second derivative because we found our absolute minimum already. Okay, so then we said we want to do this again where the distance between A and B is only 3 kilometers. So same kind of setup, just we changed the distance between A and B to be 3 instead of 10. So all we've done is we've just changed this constant here, so everything else is going to work out to be pretty much the same. So our derivative is going to be the exact same because all we've done is change a constant. So we'll still get that critical point at 15/4, but now because we're looking at this where x is going to range between 0 and 3, 15/4 is outside of our interval. So we're not going to be interested in it when we go and we look for our absolute minimum. Okay, so to find our absolute minimum, we're just going to go and put our two endpoints back into the original interval, and we see that the cost is lower if we just have the cable go from the lighthouse all the way to the point B. Now, for interest, what I did was I also went and included the cost of 15/4. And what we see is that the cost of going to 15/4 is actually lower than the cost of going just from the lighthouse straight to B. And that seems really weird. So let's go and see why that's actually going to happen. So 15/4 is 3 3/4. Well, if you put x equals 3 3/4 into this, what you see is this last term is going to be giving you something negative. So in terms of the cost function, this would actually be cutting money off of the cost. So the way you could think about it is that you'd be getting money back by going and putting the cable past B and then going back along the shoreline. And that doesn't make any sense for what should be obvious reasons. So this gives us an illustration of why we need to be really cautious about what we're doing when we're doing these kind of problems and not just proceed blindly. Okay, so the next example that we have. So we're going to take a point P that's going to lie on the curve y equals x squared, and we want to find the point on that curve that's closest to the point 18, 0. Okay, so the thing that we're going to want to minimize here is going to be the distance function. So the distance function between any 2 points is given by x1 minus x squared all squared plus y1 minus y2 all squared. So the difference in the x values squared plus the difference in the y values squared. For us, we're dealing with the distance between the curve and the point 18, 0, so we can put 18 and 0 in for a pair of the x points. Now, we're going to have to minimize this function, but I don't really want to minimize something with a square root in it, so what I'm going to do is cheat, and I'm going to go and just take a different function which is going to be the square of the distance function. So I'm going to call that capital D, and I'll come back to this in a minute as to why this actually works and gives us the same answer. And then we also have the constraining relation that y is equal to x squared. So we'll go and put in x squared for y. And then when we expand everything out, when we write it all out, we'll get that the thing we want to minimize now is going to be x minus 18 all squared plus x to the 4. And from this we could go and find the derivative to be 2 times the quantity 2x cubed plus x minus 18. And we could go and find pretty simply that this is going to be 0 at x equals 2. Okay, and then we could also go and find our second derivative, which is going to be 12x squared plus 2, and that's going to be positive for every x value, and particularly it's going to be positive at x equals 2. So it tells us we found a local minimum. Okay, so then what we're going to do is we're going to put x equals 2, we're going to take that and put it back into this distance equation, and when we, well, I guess we'll put it back into the original one. And when we put 2 and I guess also y equals 4 back into the original equation, we'll get that the distance between the point 24 and 18, 0 is 4 times the square root of 17. So just a little bit more than 16. Okay, so why did this work? So this red dashed line, which we can see here is a bit over 16, is what we got for the final answer. And this blue curve is the original distance function. So it's this square root of x minus 18 all squared plus y squared. Okay. Well, then what we did was we squared everything. So what we can see is the minimum point of this function is still occurring at x equals 2. So here what we have is that this minimum value is occurring at x equals 2. The reason why this worked is that if I have some value here at 2 and it's smaller than the value at 0, when I square the numbers, I've got a positive value here and I've got a positive value here. So this one is going to get, everything's going to get squared. And if the smallest value is at x equals 2, after squaring things, the smallest value is still going to be at x equals 2. The other thing that we've got is everything is positive, so we don't have to worry about anything weird with potentially negative numbers. So when we took the square root, we didn't change where the minimum was occurring. We changed what all the values are, but we weren't necessarily concerned with what they were. We were concerned with where the minimum was. And then once we found the minimum, we went and put it back into the original function that we started with. Okay, so I think one more example, maybe two. So let's go and take a rectangular flower garden, and we'll fix the garden to have an area of 30 square meters. And then we're going to surround it by a border that's 1 meter on 2 of the sides and 2 meters on the other side. And what we want to do is come up with the dimensions of the entire structure, so the garden and also the borders, that are going to minimize the total area. Okay, so we'll define all of our variables as this. So we'll have side lengths of W and L. So L and W will be the side lengths for the original garden. And then the side lengths of the entire structure will have L plus 2 and W plus 1. Okay, so then the function that we want to minimize in the end is going to be L plus 2 times W plus 1. And the constraining relation that we have is that L times W is 30. So L is going to be 30 over W. And then we'll use that to go and eliminate a variable from the original function A. Okay, so when we do that, we'll get that the function that we're going to have for the area as just a function of the variable W is going to be 2W plus 32 plus 30 over W. And when we find our critical points, we'll get that the derivative is going to be 2 minus 30 over W squared, or 2 times W squared minus 15 all over W squared. So a couple of critical points. The first thing that we see is that our derivative doesn't exist at W equals 0. We'll ignore that one for physical reasons. And the reason that we will ignore it is because if W was 0, that doesn't make any sense. It would mean that the width of the garden was 0 meters. Okay, so then we're looking for the places where the derivative is 0. And the derivative is going to be 0 at square root of 15, plus and minus. We'll ignore the negative one also for physical reasons, because that would mean that the width was negative, and we'll mandate that any length be positive valued. So that tells us that the only critical point we're going to be interested in is positive square root of 15. And when you're doing these kind of problems, you do need to concern yourselves with all of the possible critical points. So here we had 3 critical points. We had w equals 0, w equals minus square root of 15, w equals plus square root of 15. And we were just going to discard 2 of those for physical reasons. Okay, so then what we need to do is look at the second derivative. We see that the second derivative is 60 over w cubed, and when we evaluate that at our critical point of plus square root of 15, we get something positive. So it tells us that c equals square root of 15 is a local minimum, and that's going to give us the smallest possible area. So the smallest possible area that we'll get after putting square root of 15 back into our area function is 47.5 square meters. Okay, one more example. So we want to find the length of the shortest ladder that can extend from a vertical wall over a fence 2 meters high, located a meter away from the wall, to a point on the ground outside of the fence. Okay, so a lot of words, but let's go and put in some symbols to try and make things make some sense. So we have this point X that's sitting over here on the ground. We have a fence that is 1 meter away from this wall. Our fence is 2 meters high. Our length of the ladder is L, and then the distance from the fence to this point X is going to be given by Y, and then we'll also take this angle theta in here as well. And what we can do is we can go and we're going to go in, maybe for no apparent reason, put in another triangle. So the reason for this is that we need to get an expression for the length of this ladder, and we can do it in terms of a couple of triangles. And what's nice here is that we're going to have similar triangles going on, so we can take advantage of ratios of corresponding side lengths being equal, and then also some sines and cosines as well. Okay, so the function we're going to want to minimize is 1 over the cosine of theta plus 2 over the sine of theta. So where are these parts coming from? Well, the length, we're going to get 1 over the cosine of theta is coming from this part of the length of the ladder. And then 2 over the sine of theta is coming from this second half of the ladder. We could go and find our derivatives. And again, I've gone and taken care of it for us. So we get that our derivative is going to be 2 times cosine cubed of theta minus a sine cubed of theta all over sine squared times cosine squared of theta. And we're going to require that our critical point has to be in the range 0 to pi over 2, so inside 0 to 90 degrees. Anything more than that doesn't really make any sense, because if this angle were bigger than 90 degrees, the ladder would be going this direction and not actually hitting the wall. Okay, so what we need is an angle so that 2 cosine cubed equals sine cubed. The other thing that we could say is that if our angle was 0 or pi over 2, well, if the angle was pi over 2, that would mean the ladder's going straight up and it's not going to hit the wall. If the angle was 0, that means it's going straight into the ground and it's not going to clear the fence. Okay, so we're looking for where the tangent cubed is 2. Something else that we can observe is that the secant squared is 1 plus the tangent squared. So we can solve for cosine and also sine and get these two relations for the cosine of our critical point, sine of our critical point. And then we're going to take these values and we're going to put them back into the original length expression and get that the ladder has to be about 4 1/6 meters long. Okay, so one thing that I guess I'll say to maybe quell any concerns is that questions like this are much more than I would expect you to do on a test. The kinds of questions I would expect on a test are maybe much more in line with the first couple of examples. The last one, it's more of an illustration of some more complex kind of problem solving that we could do, but it's more than something that I would expect you to do on a test. Okay, so one thing I want to do to just wrap up is I want to show you how you could use Sage to go and solve these kind of problems. Okay, so we have this function, or we have this this question, and I'm going to go and solve it in Sage as well. Okay, so we said that we have the variables L and W, and we have that the area of L and W is equal to L plus 2 times W plus 1, and we also said that L as a function of W was equal to 30 over W. So we could get A of L of W and W. All right, so that would be our area expression for W. Okay, so then we'll get our area prime of W is A of L of W dot diff of W, and I want to print A prime of W. All right, so that's our derivative for the area, and let's factor it. All right, so exactly what we just had. Okay. So our critical points will be places where we're going to solve A prime of W equals 0 for W. So let's print our critical points. There. And in this case, what we see is that, yes, the W value that we get is plus square root of 15 and minus the square root of 15. Okay. Okay. So we'll also go and take our second derivative, so A2 prime of W. We'll factor it. Made it harder than need be, but sure. Simplify. No. Okay. There. Okay, so that gives us our critical point at the one we're concerned with. And what we see is that we get a positive value. So we get that our second derivative evaluated at the critical point square root of 15 is something positive. So that tells us we have a local minimum. And the last thing I'm going to do is print the area of L. So our square root of 15 is that critical point, square root of 15. A of square root of 15. There we go. Okay, so about 47 and a half, and that's exactly what we found, was that the smallest possible area we could get was about 47 and a half square meters, and that's what we wind up with for our final answer. All right, so it also gives us a nice illustration of how we could use Sage to go and help us solve some of these kind of problems. Okay, so I think that about wraps up this one, and I will put a worksheet up in WoW Courses and see you all in the next video. Bye.